tool, but we may be bringing in a third machine. And we could talk and see if we could get maybe an instrumented tool or something like that to
Or
partner
if
with you guys.
if you wanted us to provide some sensors and Rick Finney out at MR Tool puts them in, we'd be happy to donate the sensors, and then we could plug right in.
That is he. Yeah, I spoke with Jerry earlier today, and they've got 4 tools that are potential. I don't know
We
you know.
did a couple of their tools in the past. We helped design some of the shot glass. If they have that shot glass, it has sensors inside of it. That might be a possibility.
Very good. And LSR, so that would show well,
And there
for
was another tool that we were working on, and it was maybe going to be running at another show we talked about at one time. So I think
good.
it's a resin manufacturer's tool. I can't remember which resin manufacturer it was.
Oh, okay. I'll check into that. I plan to call them back again this afternoon. So I'll start some conversations with that and then get back with you as well.
Right, right.
Good. Thanks for bringing it up. I'm glad I brought it up.
Very good. Well, I think we're right on time here, so I think we'll go ahead and get started. I think we're ready. So thanks everybody for joining. I know you can see and hear all of us. At the top of your screen, first off, myself, I'm Bennett Howard, technical sales for Sodick injection molding machinery. You've got Len Hampton, our national sales manager as well, at the top there, and then our host and also technical sales is Weston Harbaugh from Sodick as well. He'll be handling kind of the Q&A and kind of guiding us through this process. So again, thanks everybody for joining. We are lucky enough to have the folks from Kistler Group here. This is their second presentation with Sodick and Friends. So thanks, gentlemen, for coming back here. As Len mentioned, the first was very well received. So excited to learn some more today. So that said, today's presentation is titled Cavity Sensors as an Enabler of Innovation. And we've got Florian Pickel online here from Switzerland. It's 8 o'clock there, so thanks for staying up, Florian, to teach us some things here, and along with Curtis as well, Curtis Crick in South Carolina, I believe. So that said, I think Weston, I'll hand it back to you real quick, and we'll get started here shortly.
Yeah, thanks, Bennett. Appreciate that introduction, and welcome, and thanks for joining us today out in the crowd here. As we hear from Florian. Let's just a couple minutes cover some quick logistical items for you. First, to update Sodick and Friends, this is the 29th of the series. It started back in March of 2020. Doesn't look like there's going to be any slowing down either. So over the next couple months, we have a great lineup that will include Artie Abbott, Nexus, and more. So watch your email inbox, I guess, for invitations to those. Secondly, and very importantly, let's listen to Florian and allow him to present his full presentation today before we get into any Q&A. And during that time, during his presentation, you can submit any questions that you have through the Q&A portal on the lower right-hand corner of the WebEx screen. And if you will, please direct those into the host. As the host, I will compile those, and at the conclusion of the presentation, we'll go ahead and start sharing those with Florian and allowing him time to answer each one in order of how they were received, and give him enough time to answer each of those. So I guess with that, Florian, this is all your time now. Go ahead.
Well, perfect. Thank you so much for the great introduction. Also, would like to thank you, Sodick, Weston, Bennett, and Len for having me again. Second time, as mentioned. I think it was roughly 1 year ago where we had the first chance to introduce and share some content. My name is Florian Pichel, and I'm the head of business development for the business unit Plastic. I'm located directly here in Switzerland. And in the next 40 45 minutes, I will introduce several topics which I personally like a lot. It will be in the process monitoring with in-mold sensors and its instrumentalization, as well as some practical use cases and potentials for your plant. The agenda for today will have different blocks. So initially, I will start with a little bit background, challenges, motivation. Then, nevertheless, I will have a small theory block, which is introducing the fundamentals of in-mold process monitoring, especially cavity pressure monitoring, the creation, how it's done, and what you can derive out of this. And then finally, I have several videos which are showing the potential application examples and some use cases, how it is done in real time and also in your production, on your production side. The application example will have a focus on how in-mold sensing can improve mold qualification, process baselining, enhance process monitoring, and a little bit about process control, which might then also be interest when you have some regrinded or used material, and you will achieve with this some process stability. Before we start, I would like to have one interaction with you. Here I have a small Menti code. Please scan the QR code and rate. What is your background? How do you evaluate in-mold sensors? Do you think it's useful? Do you think it's not useful? And the second question I would like to have is, what is your knowledge level for in-mold sensors? The most easiest way is to take your smartphone, scan the QR code, and then you can easily submit it, or go to menti.com, enter the code 67932756, and then I will get some reply. In the end, I will share the results. This is just for me, how to get a feeling if you already get in touch with it and not. So, where to start? We are still in the injection molding process, and I think the majority of you know what is the job. We have some materials, some granulate. We are using process equipment like an injection molding machine. We are having different peripherals like cooling, handling, and so on. And we have an injection molding tool. And the primary goal is really to focus and to produce parts which are fulfilling the quality, but also have a very good compromise between production costs and the achieved quality. In this picture, there are not so many items illustrated, but here you can see different interactions. On the right side, you have your customer. He is requesting the highest possible quality. You also are in contact with your quality department. And in the middle, you have the shop floor, and the shop floor is targeted to keep the production costs very low. This is your internal view. In the past weeks, months, as well as years, there were also external factors who are driving your production. I'm currently not 100% sure about North America. Currently in Europe, we are facing a lot of environmental awareness. We have new regulations who are forcing us to integrate regrinded material into the product. That means the process will get a little bit unstable compared to virgin material. If you are injection molder for medical devices, you have a very regulatory landscapes. You have the FDA, you have the new MDR, which is also requesting more documentation, more items. But you also have some new trends which came up in the last year. That means with digitization, with interconnected devices, you're trying to save money. And this is a really, really challenging environment where you have to compete and have to at least fulfill your business processes. How to achieve or how a process can be monitored can be clearly seen here. Here, I'm collecting 4 different methods, how an injection mold can be monitored. The most classical one is the so-called statistical process control. It's the most common one. You are producing, you are taking out parts, you're doing the measurements, and then you're collecting the data in a control chart. To mention one disadvantage is sometimes it's happening after your production. And if you realize that some days after the production, the mold is dismounted, you have a very high scrap rate, then you cannot fulfill your customer orders. Another one, which is also very common, is to monitor specific machine parameters. Here, it's, well, very common, very classical approach. What you can do. To mention one disadvantage is that you get a lot of information from the machine, from your process, but one item is still missing. It's the information out of the cavity directly where the part is created. And this is the starting point where I'm jumping in, or different other suppliers. We have here so-called cavity pressure sensors, which are directly integrated into the mold. You are monitoring the processes, and you get direct information also for high cavity molds. One disadvantage also to mention is that you need additional investment for the measuring chain. Last but not least, this is a combination of machine parameters, process data like cavity pressure, and some mathematics. With the combination and linkage between machine, cavity, as well as quality data, you are creating so-called mathematical process models or quality models. To mention one disadvantage is that it takes time, because the basis is one design of experiment which need to be done. And as you know, having different steps, this takes time, and it's very cost expensive, but it can be found very often in the medical industry. What is cavity pressure in a more holistic view? And here I would like to draw the combination between inline and offline process monitoring. On the left side, you see the machine. You are setting critical process parameter, which you have defined, and which are affecting critical quality attributes. On the right, you are producing the parts, you're taking out the parts, you're doing the laboratory measurements afterwards, and then you're getting the results. In between, you also have to focus on, is my tool capable of producing the parts? And is my process capable of it? Classically, you're not only having one process or process setting, you are having a process window. And with a different process window, you also get the same question about, is my tool capable? Is my process capable? And what will be the resulting outcome? To integrate cavity pressure monitoring, this can be seen in this picture. You have the mold, you are you're installing sensors into the mold. You're getting direct information about physical properties like pressure and temperature for each cavity directly, for each machine setting. And you can link the settings as well as the process value directly to any quality attributes. Another information which can be taken out of this approach is that for each cycle, you can have a look on how balanced is my mold. That means how to answer the question, is my tool capable? Do I have any internal or external effects affecting the molding approach? Having a look on cycle by cycle, you can derive information about how capable and how stable is my process. Because if you always have the same physical properties, the same maximum pressure, the same other KPIs derived from the in-mold cavity pressure sensors, you can be sure that in the end, your parts will also have a very stable feature and value. This picture here will be, again, one of the structuring elements, because it's not always about talking about the sensors. We will also have a look on different features and use cases which can be applied. We will have a look on process monitoring, how cavity pressure can be used for automated part separation directly in the process. We will also, or I will also show you a little bit process baselining, how a reference curve or cavity pressure curve can be used if you have a mold transfer. And last but not least, a little bit or a small outlook how a process can be controlled based on cavity pressure. And here I would like to mention an automated switchover based on cavity pressure, as well as an automated balancing for hot runner controllers. Let's start with the fundamentals, and I would like to start with a short overview about which pressure can be found in an injection molding process. I have two different areas. I have the machine here on the right, and I have the mold on the left. Here I have an hydraulic injection molding machine. We are starting with the pressure at the oil, which can be seen here on the right. If you proceed along the flow path, you can derive information for the molten or melted material in front of the screw, in front of the nozzle. The pressure can be either measured directly with appropriate sensor technology, but classically, normally, you're getting the information out of the machine with the calculation of different machine parameters. When we talk about in-mold pressure monitoring or in-cavity pressure monitoring, we have to focus on in the cavity, and this is seen here on the right. Between the nozzle, the screw, you have the gate. You can have a lot of external effects or effects affecting the flow, affecting the material, affecting the temperature. In the cavity itself, we are having different locations where a sensor can be placed. The classical approach is to place the sensor very close to the gate. We call it post gate. Here you get some information about the injection phase. But you also have the possibility to place sensor or sensors over the flow path. Here, what is illustrated is a sensor in the middle of your part. For example, if you have a very long part using cascade molding, then it makes sense that you have a triggering in and you get signals out of this when the melt is overflowing to control the cascade. And last but not least, there's one location which is called end of fill, and here you're placing the sensor at the end, and this is classically used for shot monitoring and some other quality attributes. When we talk about cavity pressure itself, why is cavity pressure so important? And on the left side, you see the classical cavity pressure profile, how it looks like when you're doing the molding. It's pressure over time. And out of this picture, you can get different information. So at point 1, you are starting the cycle. The melt is entering the cavity, but it has not yet reached the sensor. At point number 2, the melt is reaching the sensor, and this is really the triggering point where the curve is increasing. From point 2 to 3, you see the sharp increase. And after point 3, you see a fully different curve distribution. And at point 3, you can derive the information that at this point, you had the switch over directly at the machine. The cavity is roughly filled. You have 90% filling, volumetric filling, and or full filling. You go into the compression phase, which is the green area between 3 and 4. At point 4, the cavity is full. The material is cooling down. You reach the maximum pressure in the mold, in the cavity, and from point 4 to 5, you are having the cooling, you have the compression, the holding phase, where the volumetric shrinkage is monitored and applied. And point 5, the gate is frozen, no material can be entered anymore, and you see a sharp decline in the curve. And last but not least, at point number 6, you have end of cycle. You open up the mold and the part will be ejected. In this short introduction about the meaning and also the information what you are deriving from this cavity pressure curve, you can clearly identify the different phases of the injection molding process. So for example, you see the injection phase, which is somehow set by injection speed, melt and mold temperatures. You have the compression with the green area. Here it's a switchover point, as well as some temperatures, and the holding and packing phase. And this is set by holding pressure, holding time, and influenced also by different temperatures. When we talk about the relevance and the meaning of cavity pressure, it's not only that you get information for your process. You can also get information or know information that each of the different phases will have an impact on your part quality. So for example, in the injection phase, when you're injecting too fast, you can burn the material, you can create some surface defects, which is not in line with the requirements. In the compression phase, which is mainly responsible for setting the filling status, also having a surface forming, and is responsible for flash and the fill status. If you understand this, then you can easily compensate such failures automatically. And last but not least, the holding phase, I initially stated it. It's the compensation and the monitoring of the volumetric shrinkage. Here, this phase is mainly responsible for weight stability, for geometrical stability, but also the length of the holding phase will have a direct impact on your part quality, because if you're ejecting the part too warm, you will know it, you will have some inner tensions, you have some inhomogeneous cooling, will then finally lead to warpage at your part. This is information what you get out for your process, but also for your quality. If I look on the impact of different machine parameters, and I think you also know that during or for an injection molding process, you are having different machine parameters like injection speed, temperatures for the hot runner, for the mold. You have different pressure levels, the holding pressure, the back pressure, as well as the temperature for the barrel. And all of these different machine parameters can be visualized with cavity pressure. Temperatures are changing the viscosity, and a change in viscosity will also have a change in the appropriate pressure curve. Changes will shift the appropriate pressure curves either to higher level and lower levels. Another item which can be made visible is the holding pressure. And if you look at both graphs, you see that the blue one is having a higher level and the green one is a lower level. And if you remember previous slide and where I stated that the holding phase is responsible for geometrical stability and weight stability, you can assume that the part for the green line will differ compared to the blue one. In worst case, it's not fulfilling the specification, it's not fulfilling the specifications for weight, and there might be also a high risk that you will have some voids in the parts. Another item is the injection speed. You see here that with higher injection speed, you are filling faster, you are changing the curve profile. This can be also clearly seen. You see also information about an optimal switchover point, which can be derived from this information, but you can also get information about the maximum pressure, which then can be finally correlated with the clamping force and so on. And last but not least, the last one is the switchover. When you change the inspection speed, you should also have a look on the switchover point. If you have a higher injection speed, then you should also adapt the position of the switchover accordingly. In worst case, what could happen is that switchover comes too late. Then there might be a risk that you're overpacking the mold, you're damaging the mold. And when the switchover comes too early, then you are not having a full cavity. The holding phase cannot compensate the shrinkage, and you will have some geometrical deviations for the part quality. This was the fundamental block where I was talking about. Let's shortly talk about the instrumentalization for my cavity pressure monitoring. And I would like to integrate the sensors directly in the mold. Here I have a small video, which you can see right now. You see here the cavity, you have the card, you see the integration of the different sensors. Talking about different sensor types, we have direct sensors, indirect sensors. The direct one can measure both pressure and temperature. The indirect sensors can be placed behind one ejector pin. This is one classical, very common approach. But we as Kistler also have a third variant, which is a so-called contact-free measurement. And here you can place the sensor direct behind the cavity wall, which then can be finally used for optical parts. over the deflection of the wall, you can measure the same principle like when you're using a direct cavity pressure sensor. Where can cavity pressure sensors be applied? And here I have another video, and this lovely describes what can be seen. You have here the mold in the heart of the injection molding machine. You have a data acquisition system. The melt is entering the cavity is filled, the transducers are recording it. You have a real-time monitoring of the in-mold cavity pressure, and can directly derive information about what's happening directly in the mold. One of the benefits are really that it's not R&D anymore. It's really common in serial production. You can get 100% process monitoring, and you can easily get the data for the machine with a charge amplifier or appropriate process monitoring devices, which is illustrated here. And here you have our process monitoring device, the so-called Comoneo. How to read cavity pressure data, and this is one of my most loved pictures. This was created in our application shop. We were producing some parts for our production. This is the part. We integrated 4 different sensors. The gate is here. We have one temperature sensor, which is very close to the gate. We have one contact-free sensor, which is a little bit in the middle. We have one indirect sensor, which is placed here, and we have a pressure sensor here, roughly end of fill. We have temperature, we have pressure, but we also monitored different machine signals, which are the blue ones. Curve number 1 is the screw travel here, and the other item is the hydraulic pressure. And if you look at the screw travel during the injection phase, as well as the hydraulic pressure, you can see the direct correlation when the melt is entering the cavity, when the melt is entering the sensors. And you can clearly see that with the analysis of the location of the sensors, that the temperature sensor will generate the fastest signal here. This is the classical shape of a temperature transducer. When the melt is overflowing it, you have a sharp incline, and then over time you have the measurement of the contact temperature of it, of the melt. If you look at the different locations, you have a flow path dependency. That means that the pressure will drop over the flow length, and this can be also clearly seen here with the different curve. The blue one and the violet one are having a much higher level than the green one, and the green one is the 6184, which is end of fill. You can also see the information where at which time the machine is doing the dosing. And if you have a look at this picture, you can also derive the different information for the filling, the packing, the holding, but also for the recovery of the machine during the different phases. How can it be used for mold acceptance? And this is the next approach. Initially, I stated that first, it can be used for tool acceptance. That means with the transparency in each cavity for each cycle, you can derive information about the produced mold. You can see how balanced my mold is. You can also derive information about the cooling, the heat transfer for each cavity. Is it homogeneous or not? But if you have a focus on process development, you can directly see if the machine is producing the same procedures for each cavity. Here it's a little bit more, here it's illustrated again more in detail. You have the case number 1, the machine is injecting, you have some flow resistance in cavity number 2. Classically, cavity number 1 is filled much faster than cavity number 2. And the deviation can be clearly also seen in the maximum. The black one is the curve for cavity number 1. The blue one is the curve for cavity pressure number 2. If you have some problems, some issues, like for example, that one gate is broken or some cavity cannot be filled, you can also see it directly. And because, as you can imagine, the black one will have a pressure increase. And for the second cavity, no melt is entering into it. There will not be any recording for cavity pressure. This is one approach, But there are also tools on the market where you can use the different information and the review information. What need to be done if you have to change the steel again. For example, we also have one software which is calculating based on the recorded data what need to be done, and this can be directly matched with the part quality. What you can see here is tool capability run. We recorded the quality attributes, we recorded the machine process data, we measured the data, and based on the created data, we could give an estimation which cavity need to be improved to have a stable mold for your final production. How can it be used for process baselining or reference curves? This is the next item. This is one practical showcase on the right side right now. You can imagine that if you have a mold maker or a different supplier who is setting up the process, the mold at plant number A, he's using a different machine, different settings. And then you are relocating the mold to your final production plant. You are not having the same machine, or even if you have the same machine, you will have some deviations. The big challenge here is really what needs to be done to find a stable process again. And here cavity pressure can be used to come back to your process settings quite easily. And this is done like this. At plant A, you have recorded your reference curve, your process is stable, the parts are okay. You are recording here the reference curve, the cavity pressure curve. You're transferring the mold, you're recording on the new machine. You can see deviations coming. Yeah, the root causes can be various machine, different geometries, temperatures. But with the help of the cavity pressure curve, you can take this curve and transfer the process quite easily. How is this done? You analyze each phases of your injection molding cycle. You have a look on the injection phase. You're adjusting the injection speed. You're adjusting the switch over point. You have a look on the set holding pressure, back pressure, end time. And your approach will be done iterative to find and to match the curve over the different cycles. And you will achieve this curve after different steps. And your goal is that at the new plant, at the new machine, the cavity pressure curve will be on the same level like you have created at the different supplier at the different location. How to work with, how to use cavity pressure for the process development and optimal working point. The classical common approach, what we can find or which is common, is to do it try and error. You get the machine, you set it up, you use the different machine properties, set it up, and then find a stable process. A different approach can be done with so-called process models. Here you are using design of experiments. You are fully analyzing the process room with the help of the cavity pressure sensors. You're collecting the data. You are collecting the parts property, creating the quality model. And with the help of this, you can create neuronal networks, and this can be then finally used for the optimum working point. This is the same picture from previous slide. Imagine if you change injection speed, switch over point, all the different elements, what I have recorded here for one settings can be made visible. What can be also taken when I'm talking about the working point, you have the potential to use statistical models where you can run simulations. On the right, you can use the set machine parameters. You can change the set parameters, and with the correlated and derived information, you can estimate what might be the impact of my part quality on the right. For example, here I changed the holding pressure. And if you look at the points with higher holding pressure, you have a higher compensation of the volumetric shrinkage, and you will have a more or less stable process, which is then resulting in stable part quality. How can it be used for process monitoring? This is a different approach. Here you can use different evaluation objects, envelope curves, or as well as process models. The video lovely illustrates how it is applied. You see here the recording of the cavity pressure curve. Systems are monitoring the cavity pressure directly in the process, in the cycle with these boxes. And with the height and the adjustment of the boxes, you get the information if my part is stable or not. Here you have one example where 2 cavities was not reaching the allowed pressure level, and a sophisticated monitoring device automatically give a signal to the machine so that the parts will be automatically separated and scrapped. Another item which I would like to introduce, and this is a little bit referring to the title, How to Drive Innovation. And this can be seen here with process models. You can integrate this sophisticated process data into machine learning. You can create process models with different heights and values. You can record it. Each of the different cavity pressure curves are having impact on the part quality. This can be also directly done with the process monitoring devices. In real time, process are classified afterwards because you're doing the measurement for each cycle, for each DOE. You're measuring the items, and then you're creating the mathematical models, which is then here. And with the help of the classification, you are really capable of driving innovation at your shop floor, because with information you can generate predictions models based on artificial neural networks, and this helps you to do simulations, to do process analysis, but also to improve the process with this optimized database. In real time, this would be the graphical user interface for our device. Here we have different parts qualities, and what can be derived right now. You're not getting only the information if the part is good or bad, but you get also a quality documentation. And the quality documentation can be then also finally then used for batch release, your supplier or customer documentation. All the data what we are generating with cavity pressure are stored. You are not only doing a cycle view, you can get information over your whole production time. That means, for example, if you have a night shift and you don't know what happened in the night shift, have a look in your historical data, have a look on the different phases, and you can clearly see if something went wrong, something was changed. And this is really reducing the risk that bad parts will be sent to the final customer. Another item which is referring to the back is a little bit talking about material efficiency. When you do the process monitoring, you have the analysis, you can detect variations in material, in process, in temperatures, in human handling. You can analyze this, you can detect it, and in combination with process control, you can also derive material efficiency. Because imagine, how is material efficiency defined? On the one hand, it's a reduction of scrap. On the second, it's a incorporation of used material. And with the combinations of advanced monitoring devices, in-mold data, more machine data, you're capable of addressing this question quite easily. How is this done? Can be seen in this video. You're monitoring the deviations right now. Changes in material and the process can be detected automatically. That means your shop floor can take actions right now, but you also have the chance that parts will be automatically separated if parts are not in the defined range and in the specification. And this is then also the starting point talking about the control. And here I would like to have a short view on the switchover control based on cavity pressure. I think each machine is really capable of doing the switch over individually, but this is normally or classically done by a screw travel. But imagine if you have the information from each cavity and you know that you would like to do the switch over at a certain pressure level, why not using the in-mold data to send it back to the machine that at a certain pressure level, which should be reached for each cavity, that the machine will do automatically the switch over. And this is again illustrated in this one. This is also the picture what I showed initially. Case number 1, you have a slight deviation. You can imagine that the pressure level is on the same level. You can easily apply a pressure threshold right now that if you reach this pressure threshold at cavity number 1, do the switch over, or you can also generate a forced switch over if the cavity is full. This is really the benefit for protecting the mold. By protecting the mold, in case number 2, this can be seen quite easily. The gate number 2 is broken, no melt is entering. In worst case, you're overpacking cavity number 1, you're generating flashes, you're generating plastic deformation of the steel, and this is really not wished. How can this be applied? Like here, I mentioned pressure level. Here I have different application examples how it can be applied. For a 4-cavity mold, you can easily apply execute the switchover based on cavity pressure by one single channel, all channels, or a combination. And the combination you have seen in previous slides where you know at which cavity the pressure is reached latest, but you also have the combination with enforcer trigger when you apply the cavity pressure approach for the cavity where there is a high risk for overpacking. You also have automatic algorithm controls, which can be found on the machines or in sophisticated process monitoring device. And with a combination of this, you can also generate some benefits. And here we also have some trials which can be seen here. This was one of our bachelor thesis, what we have done. We investigated the impact of different switchover procedures. Here on the left, you have the machine. Then we are using the so-called automatic manual one in the cavity pressure switchover threshold. And you can clearly see that the cavity pressure is one item for process monitoring. But if you look at the switchover volume, which is this one, with the cavity pressure, you see that the switchover volume was much higher compared to the previous one. This is one view. What is the impact on my process? This can be seen, or on my part quality. This can be seen here right now. The red one is my weight and the blue one is my shrinkage. And with some more focused cavity pressure threshold, you can change your weight stability to a higher level, as well as also shift shrinkage to higher levels when you use in-mold data. That's not only about process control. You can also derive information from your whole production plant. This is seen here in my last video. We are not only collecting the data, the collected data can be then finally transferred to a third-party product like a MES or data storage or data lake. You can easily access the information. You can run predictions. You can run production planning approaches, but you also derive information about different machines, different locations quite easily when you use all of the data for the for your production plant monitoring. That's from my side. Let's come to the last page, a short summary. What have you seen? You see different applications and application examples for monitoring piezoelectric sensors. You saw different sensor types. You saw how a sensor is instrumented or installed in the sensor. Get a little bit the feeling for the cable and connection technology. Then you have information about the monitoring device. You get a lot of information for your process. You can real-time do process monitoring. You can do a good bad part separation. You get alarms. You can make everything transparent and control your production shop floor. You can also drive innovation with it. You can analyze the process on a holistic approach with design of experiments. You can use the sensor data for, artificial intelligence generating, what else, driving efficiency increases. But you also have a permanent database because the data are not senseless. You can store the data for your quality documentation, for your regulatory appliance, for what else you want to have. You can store the data or send it directly to MES or different storage, and you can access the data everywhere whenever you want to have. That's from my side. If I created some interest for you, I also have some additional Kistler dedicated marketing material. If you would like to learn more about the technology and the basics of cavity pressure, we created a technical white paper. This is lovely describing the physical and the rheology behind. Have a look on our webpage or screen the QR code, then you will be redirected to it. If you're interested in getting to know more about our sensor technology, on the left you see a brochure about our sensor portfolio and connection technology. If you're interested about data acquisition systems, like what you can see here, our Communio, please have a look on the QR code. Last but not least, we are also working with different industries. For example, if you would like to get to know some insights for your medical production, we have a dedicated medical device manufacturing, which is not only addressing plastics. Here we also have different elements for assembly testing, joining, as well as vision inspection technology. And if you're interested for a basic plastic processing, please take the QR code on the right. On the right above, you have seen Kistler. Who are we? As mentioned, we are a Swiss-based company focusing on the production of piezoelectric sensors. Our motto and slogan is measure, analyze, innovate. And I hope that the slogan was represented in my presentation. Where can you find us? Quite everywhere on the planet. As mentioned, we are located in Switzerland as a headquarter, but we have more than 60 locations worldwide. We have more than 10,000 customers as a Kistler Group, not only plastics. We have more than 700 applied and granted patents. We are working closely with R&D and universities, but we also have a very good relation and cooperation with our industrial processes. And how big is Kistler? We're having more than 2,200 employees as a group. Who is Kistler itself? So I'm coming from the plastics industry, but Kistler is not only plastic. You can find Kistler in race cars. You can find our sensor technology supporting professional sports like Olympic swim teams, athletic teams. You can find us to make speed trains more safer. For example, we created a crash wall for trains in China. And as you have seen, we also guarantee high production efficiency and transparency with an application of in-mold sensors in the injection molding process. Who are we as well? I'm coming from plastic, but as mentioned earlier, we're not only having plastic, we're also having different industries, which can be seen here. We have assembly and testing represented by joining. We have production monitoring for assembly steps and test approaches. We have vision control, we have fastening technology, and we are also producing test stands for different monitoring approaches. Who am I? Right now, thank you so much for listening. My name is Florian Pichel, and if you would like to get in contact with me, here you can find my contact details. Thank you so much. And again, it was a great pleasure for me having my second speech in front of you. Thank you.
Florian, well done. Thank you for that. We did receive a few questions in here to get started. So I guess without further ado, the first question is, where should we place the sensors, post gate or in the fill?
It really depends on the use case, what you would like to have. So initially you have seen the different positions. If you place the sensor close to the gate, you get a lot of information for the injection phase. That means if you would like to do a switch over control or hot runner balancing, then it's recommended. If you place a sensor end of fill and you would like to do quality monitoring to avoid shot, then this approach is recommended.
And driving to the next one here, what is the benefit of direct versus indirect cavity sensor?
So from a sensor or from a signal wise, you get the same information if you use a direct or indirect one. The big difference is that with a direct one, you're eliminating pollution, which is placed behind the ejector pin. That means gassing and material which could flow into the ejector pin will have an impact on the measurement. That's one disadvantage using indirect one. But both measurement principles are quite common in the industry, and it also really depends on your use case. And if you have the space for a direct one, and we are also producing sensors with a front diameter of 1 millimeter, then this one is recommended because then the effect of pollution can be eliminated. But if you're not having the space, then it's also quite common that you place a sensor behind one injection pin. But then you have to keep in mind that gassing and pollution will have an impact on transferring the pressure over the pin to the sensor.
Wonderful. So to summarize that, which method would be recommended? Direct or indirect?
If you have the space, then take a direct one. If you don't have the space, take an indirect one.
Perfect. With Kistler's technology, can that reduce my scrap and eliminate sorting for molded defects?
With sensor is the first level. You are getting insights into the cavity. The sensor signal can be then used, and you for sure need appropriate data acquisition systems, like for example, charge amplifier, which is then connected to the machine, or process monitoring device, which are automatically analyzing and scrapping the parts. Yes, can be automatically scrapped in real time directly after the cycle.
Excellent. Can the sensors also detect cosmetic issues?
Can you please repeat the last one?
Can the cavity sensors detect cosmetic issues in the parts?
What is cosmetic issues?
The overall finish of the surface, or how the part will look when it comes out. Shorts, sinks, some of those types of.
Okay, so surface defects.
Yeah.
Not directly, but if you have a process analysis and you're analyzing the process for the injection speed, you see different shapes of the curve. You can get information for this. Shorts can be detected because if you're not reaching a certain pressure level, then you can be sure that the short is occurring. And if you're overpacking and having a too high pressure level in your cavity, then there might be a high probability that you will have a flash. Not directly, but indirectly over the pressure level itself.
Okay. What's a measurement principle for your sensors?
It's really our DNA that we are 100% focusing on piezoelectric sensors. That means in our heart or the core of the sensor is a piezoelectric crystal. And when you apply a force on the crystal, then this crystal is transducing charge. One big advantage is that this measurement principle lasts for a mode lifetime. You're not having any impact of temperatures, like what is affecting short circuits or strain gauge. So this is really one of the big advantage. And you have a direct correlation of applied force with output.
Okay. So, what different sensors are available here? Size and measurement principles.
So initially, or in one video, I showed you 3 different measurement principles. You also had the question for direct one, indirect one. These are those ones. And the last one is so-called contact-free, which is mainly used for Class A surfaces. Here, the sensor is placed behind the cavity wall, and over the deflection of the wall, you are measuring the processes. When it comes to different sizes, we are offering sensors from a range from 1 millimeter up to 9 millimeter. And one of the smallest sensors, the 1 millimeter sensor, is capable of measuring pressure plus temperature with one sensor, and also temperature directly.
Wonderful. Thank you, Florian. There's a couple of questions left that you've answered. One is, where can we find Kistler? And I see, with your contact information there, or if they snap those QR codes, should answer that question for them.
Yeah.
Last question here so far that's come in is, what could be potential benefits through the value chain with these sensors?
So what you have seen right now is, if you integrate a sensor very early in the process, you can use the information for the mold qualification directly at the mold maker. You can see the quality of the manufactured steel. You see, or can make deviation imbalances clearly visible. All the information you get, or if this is done, then the next step is really the process development to define a process window, process point. Also, the sensor data can be used for it, because for example, if you have a high cavity mold with 16 plus cavities and you have to set the tip temperatures appropriately, then you're not interested of doing a measurement of all the produced parts. With the deviations, or with the measurement, you can clearly detect deviations during this process. And last but not least, 2 other items are really process baselining. If you transfer mold from location A to B, you can use the stored data and the signal, the baselining, the cavity pressure baseline template as a starting point to recover and to reset the process. And last but not least, what you have seen is your automated part and scrap separation with appropriate devices. So here you can really eliminate the risk that short parts will be automatically transferred to your end custom, which will, in worst case, will be a disaster in reputation.
Very good. We'll leave the questions open here for just a couple more minutes. But at this time, I want to say thank you behalf of Len, Bennett, myself, Sodick. Thank you very much for joining us again. As always, it's been very great. So,
also from my side, thank you so much for having me again. It was again really great pleasure. Thank you.
Yeah.
Yeah, Florian, fantastic job. I appreciate your time last time, and again, this time was well received, I think, from quite a few people here. So hope everybody got a lot out of it, and looking forward to hopefully partner with you guys on an LSR tool in end of March out in Rosemont, Illinois, the Plastic
Hopefully.
Technology Expo. So it looks like that's gonna go off in a big way as well. Hopefully the variant is under control and everybody can do it safely. So thanks again. We really appreciate it.
Thank you so much for having me. It was a great
Thanks,
pleasure.
Curtis. Thank you, Curtis.
Thank you.
Bennett, thank you.
Thanks,
Wes.
guys.
Thank you.
Thank you. Have a great afternoon.
Take care.
Bye-bye.